Hello and welcome back. In this slice of physics, we're going to discuss the concepts of air drag and terminal speed. If you've ever ridden your bicycle at a fast speed and tried to race, you know all about drag. It's the biggest force that you fight against when you're riding your bike. So if your bike is over here, pardon the crude drawing, but it'll serve the purpose. Let's say you're sitting upright on it and pedaling. As you ride your bike, you're moving through all this air, displacing it, pushing it aside as you go through it. And that air pushes back on you, and that force is called drag, which I'll just label with a capital D over here. So in some ways, drag is like kinetic friction. It's a resistive force that's connected to a motion, but it's also very different in other ways. So let's see what drag is. In the sense of direction, drag is very similar to kinetic friction. It's also opposite the direction of motion. But in terms of magnitude, it's different. If you remember, kinetic friction's magnitude only depended on the coefficient of kinetic friction and on the normal force. And surprisingly, it did not depend on the speed with which you were moving or the area of contact. Drag, on the other hand, does depend on those factors. So the factors drag depends on are the density of air. That makes sense. If you're going through vacuum, there is no drag because you are not going through any material. And the denser the air is, the more the resistive force will be. If you've ever tried to run through water, it's a lot harder to do that than running through air. That's because the density of water is a lot higher. And the symbol for density is rho, Greek letter rho. So we'll use that. And secondly, as we said, it depends on the speed. And it turns out that drag force is not just proportional to the speed increasing as the speed increases, but it does that in a very sensitive way. If the speed doubles, the drag force quadruples. So it's really proportional to the square of the speed. And thirdly, it depends on the surface area that's presented. And that's the reason you don't see champion bicyclists riding bikes sitting upright. They would be in a position where they are completely hunched over. So their body is more like this. The reason they do that is by taking this position, the area that they present to the air as they go through it is a lot lesser than it was before. And so they minimize the drag force. They want to go fast, so they can't really compromise on the speed. They can't control the density of the air. The only factor they can control is the surface area, which we'll write as capital A. So the equation for drag force is 1/2 times CD rho A V squared. We've already talked about these three factors: density, area, and this relation with the square of the speed. CD is just the coefficient of drag, and that's somewhat akin to the coefficient of static or kinetic friction. But the CD depends on the details of the shape of the object. But in most practical cases, the coefficient of drag turns out to be about 0.5, so this equation simply translates to 1/4 rho A V squared, and we can work with this form of the equation for all practical purposes. Okay, terminal speed is related to drag, and it has to do with drag on an object that's falling. So as a ball falls to the ground, it also is going through the air and feeling the resistance force from the air, and so there's a drag force that acts upward while the ball moves downward. And terminal speed is simply the maximum speed that is attained by a falling object if it hasn't hit the ground yet. To see what happens with that, let's take a look at a ball falling from far above the surface of the earth. So here's the surface of the earth, here's the ball that's falling, and the force that's responsible for its falling is its weight. So if I draw a free body diagram of this ball, I would have a weight vector pointing down, and initially when it's at rest, that's the only force. Let me show some velocity vectors over here. So initially it's at rest, A little bit later, it's going with a certain speed v. Now at this point, if I draw a free body diagram, I would have the same weight as before, but now I would have a drag force come in play because drag is dependent on the speed. I've got an area that I'm presenting, there is a density of the air, so there is a drag force. And since the drag force is still less than the weight in this example, the ball will continue to accelerate, speeding up in the downward direction. Let's say after a little while the speed has grown to a higher value of this arrow. So in this situation, I've still got the same weight that's acting down. And let's say the drag has now grown to equal the weight. Until drag grows to equal the weight, that there's a net force pointing down and the ball will keep getting faster and faster and faster. But once it reaches a speed at which the drag force equals the weight, now it's in equilibrium, and so there is no net force, so the acceleration is going to be 0. So as the ball falls, it'll maintain the same speed. And that is what is called terminal speed, where any falling object speeds up to that value and then cruises at that as it falls to the ground. So just for fun, let's say we take a skydiver example and figure out what the terminal speed for a skydiver would be. I'll give you some particulars. The density of air at sea level is 1.2 kilogram per cubic meter, and we will use that same value for a skydiver because we're doing an approximate calculation here. So technically, even though the air is a little bit less dense up above, it's not going to be that much different from this, so we'll just use the sea level value. The surface area that the diver presents to the air is going to be their entire front of the body, because that's how they're oriented falling in through the air. And we're going to approximate that to a rectangle, even though that's not correct, but we're only dealing with an approximation here. We're going to say this person is 1.5 meters tall. We're going to say this person is 0.4 meters wide, and we're going to treat them as a rectangular cross section, and that'll give us a area of 0.6 square meters. We want to find the speed, and at that speed drag equals weight. So if I do sum of Fy equals 0 as a condition for terminal speed, so that I've reached equilibrium, drag equals weight, and weight equals mg. So I can write this equation here as, instead of drag, I can write mass times the acceleration due to gravity, which is the weight, equals 1/4 rho a v squared. And let's say this person has a mass of 70 kilograms. Now rearranging this equation, I can get v as square root of 4 mg over rho a. And when I put all these values that we have set up over here, for this person the terminal speed turns out to be about 62 meters per second, which when you convert to miles per hour is 138 miles per hour. The reason divers use parachutes is because this is too fast. If they impact the ground with this speed, they're not going to survive the fall. But by using a parachute, they drastically increase the surface area, and by doing that, they can reduce the terminal speed to a much more comfortable falling speed. So in this slice of physics, we reviewed the concepts of air drag and terminal speed. Drag was the resistive force from air or from another medium when an object moves through it. It's always opposite the direction of motion, and the magnitude depends on the density of the medium, surface area of the contact, and the speed of the motion. And we noted that it's a highly sensitive dependence on the speed because it relates to the square of the speed. And the terminal speed was the equilibrium or maximum speed of a falling object. Thanks for watching.